I say quiz is already over. No. So what I'm going to do is I'm going to switch it around. All right. So Friday quiz, we won't have a quiz today. And next week we only have 2 lectures, so no quiz next Friday also. But then we'll have one the following week, which is week 8. And that will be the last one. Okay. Yes. I'm debating whether to have one or not. I might have one on Wednesday. It's a good question. So I'll post an announcement early enough by tonight or at least by tomorrow. So that students will know in advance whether we have a quiz on Wednesday or not. Okay. All right. Device physics of a junction field effect transistor. We can talk about that if you want. All right, let's see. Morgan's laws, logic gates, NAND building block, combination logic. Okay. So everything that we looked at so far, it's all combination logic, right? We take a combination of gates, we can combine them depending on our application, we can combine them for a specific output. Okay, so here's one such example. Output F is equal to ABC plus ABC plus C plus D times D naught plus E. Okay. So if you treat it like any mathematical equation, we should be able to take these quantities and we should be able to implement it using logic gates. And that's logic design, basically. So let's see how that would work. Okay. So how do we begin? If you were to implement this using logic gates, what would be the first step? Where if you think about this mathematically, what would be the last operation that we would perform? The addition, absolutely. So if there's addition, we can divide this into input 1, let's say V1, V2, and V3, right? So if we want to perform addition or summation, what kind of gate do we need? OR gate. And mathematical summation is OR, and mathematical multiplication is logical multiplication AND. So this would be an OR gate, but we have 3 quantities. So we need a 3-input OR gate. So this is F at the output on the far right. And we need a 3-input OR gate where we'd have A, B, C, the first quantity, and the second quantity A, B, C, and the third quantity C plus B times or AND B plus E. So let's take V2. V2 is by far the easiest, right? V2 is A and B and C, a 3-input AND gate. So we can do that here. This would mean this is ABC. You all with me so far? Right, ABC. So that's V2 taken care of. Now we have V1. V1 is ABC, but the B is inverted. So A and B naught and C. So we need another 3-input AND gate. However, B is inverted. And so I would do, let's do it here. That goes in here. And so that becomes B naught. And that's A. And that's C. And the way I would show connections is by making large dot right there. If there is no node shown, that means there is no connection. Yes. Can we expand V3 into two terms? That will come later. The question being asked was about modifying the equation, right? So we will do that after we finish this. And so this would give us A, B, C here. So the output here is A, B, not and C. We made a hash of this. Hold on. So let's come down here. Okay. So that takes care of V1 and V2. Make sense so far? All right, now we have V3. Well, V3 is comprised of 4 C plus D and D naught plus E. So if we now break this down, V3 requires an AND gate, and then also requires 2 OR gates, right? So let's do the AND first. Actually, let's do the let's do the AND first. So we have a AND function right here. Let's do it. All right, let's just do it here. Okay. So this would be C plus D and D naught plus E. So 2 input AND gate. Now we can tackle C and D and then D and E. So C and D, you can draw it like this with this is D. This would be C plus D. And then I have a second OR gate, but that requires an inverted D input. So I'm going to take this D right here, feed it to an inverter. So I get D naught or D prime or D bar. And finally, we have E. All right, there you go. And that's how you would implement that equation. All right, let's take a pause. Let me know if you have any questions. Make sense? Right. So how many gates do we need? 1, 2, 3, 4, 5, 6, 7, 8. 8 gates to implement this, right? which is fine if you have the space, but this is a simple operation. When you have really large circuits, then it makes sense to actually reduce our equation. When you have reduced equations, we can have implementation with a reduced number of logic gates. So that's what we'll do with this equation. And that's the answer to the earlier question, manipulating this equation. Okay. So if we take this equation and we'd want to reduce it, we can approach it similar to any mathematical equation. Okay. Goal, of course, is minimum number of gates. So let's take a look at the terms right here first. We'll expand these two together at the far right. So V3 can be written as CD naught plus CE plus DD naught plus DE. Okay. We're simply taking V3, the four terms, and we are expanding them. So the result is CD naught plus CE, DD naught plus DE. Now, what do you notice? When you have the same input, either multiplied or added up, we can eliminate that. So the product of D and D naught, tell me, 0. If D is 0, then D naught is 1. So 0 and 1 gives you 0. If D is 1, then D naught is 0. So again, D and D naught would give you 0. So the product of the same quantity with its inverted output would always be 0. So logical AND, meaning logical multiplication, would always go to 0. So we've eliminated one out of those four quantities. Okay, so one less input required. Then let's insert it in our equation. F is A B naught C plus ABC plus C bar plus CE plus DE. What is the most common input? C is the most common input. So let's take it outside. C times AB bar plus AB plus CB bar. Oh. Plus E. Now this is not the approach, and the reason I'm showing this is just to show you how engineers would work with designs. Okay. So we took C outside, but DE does not have a C. So we still need an extra OR gate at the end. Right? C is the most common, but it's not common to all of them. So we still need multiple iterations. Right? So we do take C outside, what have we left? So you got A, B naught plus AB plus D bar plus E. What else is common? A is common, right? So if we take A as common, what do we get? B bar plus B plus D bar plus E plus DE. So what happens to B bar plus B? 1, absolutely. This goes to 1. And so now we have reduced F A plus D bar plus E plus DE. Is a further reduction possible? Probably not. We can do it in a different way, but we cannot probably reduce this any further. So let's look at the number of gates that would be required. OR gate, and then an AND gate here, and then another OR gate here, and then an AND gate here, right? Is somebody remotely controlling my screen? One, two, three, four, right? One OR gate right here, another OR gate for A, D, and E, one AND gate, and then one more AND gate right here. Yes. And then a NOT gate. Yes. Thank you. NOT gate right there. Do we do it correctly? NOT gate. So 5 gates. What does everyone think? 5 gates, right? There's also another possibility where we can combine these two together. But let's see if it reduces the number of gates. So E is common. We can take the E outside, right? If you take the E outside, we'd have, let's say here, we can take AC outside, and then we can write B bar plus B, because we know that goes to 1. And then here it's C D naught plus E into C plus D. Can I do it correctly? E into C plus D. We could also, no, we can't combine D naught and D because E and C are different. Okay, C plus D. And so then F becomes AC plus CD bar plus E and C plus D. In that case, we would have one OR gate one AND gate, NOT gate, another AND gate. And then here you'd have a AND and an OR. So 1, 2, 3, 4, 5, 6 gates. That requires more. So that's probably not the way to go. Yes. That's a good point. So the point being made is, why can't we pull out C from the first two? So yes, we can do that. Absolutely. So we can reduce this further. And if we pull C out, we get A plus D naught. And then we get E and C plus D. So now we have one OR gate, 2 OR gates, 3 OR gates, and then one AND. So OR, and then NOT, and 1, 2, 3, 4, 5. Still, we end up with 6 gates. So, but that's a good point. We could possibly even do a little bit more at the top and not combine these, and you can pull C outside. If we don't combine it, let's See what happens. So not from there, from here. So you got AC plus C bar plus EC plus ED. And then if we take C outside, we get A plus D bar plus E plus DE or ED. That would give us, let's say, one OR, one AND. Oh yeah, that's the same as this one. We already did that. AC, CD, EC. Oh, yes, that's it. So five seems to be the most efficient. Obviously, also depends on what we have available at our end. Right? So you're performing an experiment in the lab, for instance, and you need a resistor of 2.2 kilo ohms. But if you don't have one in a lab kit, but if you have a bunch of 1 kilo ohm resistors, you combine them in some way to obtain 2.2 kilo ohms or something like that. All right, let's take a pause. Let me know if you have any questions. Does the process make sense? Right? Combinational logic design. You take different gates and you combine them to create or implement different logic functions. Okay. Yes. So, question being asked is, are there any rules? Rules about what? So the rules that we follow, like meaning reducing the equation itself. Oh, that's just mathematical. Yeah, same. It follows the same rules as the mathematical equations that we use. Yeah, yeah. But the implementation then requires logic, Boolean algebra or logic gates function. But reducing the equation, no, it follows the same rules as mathematical. Okay. All right. Then there's sequential logic, where everything takes place in a certain sequence. Okay. Combinational logic circuits are said to be memoryless or memoryless because they do not store any information. They do not have any memory. They do not remember past inputs. They do not remember past outputs. Sequential logic circuits that we look at, they actually do have some memory, meaning the output is not necessarily just due to the present input. It could also be due to the past outputs or past inputs. Okay. So sequential logic circuits are said to be memory circuits because they can store data, they can store information. Okay, they can store information. And because these can store data and the operation takes place in a sequence, we use a signal known as a clock signal to keep everything working in, I'm trying to find the right words, right phrase, to keep everything working in synchronicity. But there are two kinds of sequential logic circuits. So this would be a clock signal. Clock signal is required to keep everything working in sequence, but depending on whether it's in synchronous or not in synchronicity, then we say it's a synchronous circuit or it's an asynchronous circuit. Okay. Synchronous or asynchronous circuit. The clock signal is typically just a rectangular pulse or a square waveform. When the pulse is present, we say it's on. When it's not present, we say it's off. So logic 1 and logic 0. Okay, logic 1 and logic 0. The speed of the clock signal depends on the frequency of the signal. The frequency, of course, is the inverse of time, meaning the number of cycles in 1 second, right? The number of cycles in 1 second. If you have this 1 cycle in 1 second, then the frequency is 1 hertz, 1 cycle in 1 second. What is the frequency of the power outlets? Should go back and deduct points from your quizzes. 60 hertz. All of North America is 60 hertz. 60 times in 1 second, the power goes positive, negative, positive, negative, positive, negative. Each time it goes positive, comes back to 0, goes to negative peak, comes back to 0 as 1 cycle, right? Positive and negative half cycles. And it does that 60 times in 1 second. So it seems a fast number, but in fact, it's a very, 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 very low number. You think about our computers, smartphones, tablets, computers, desktops, laptops. The frequency of those processors is counted in the gigahertz, right? We say it's a 1 gigahertz processor, 2 gigahertz processor. That gigahertz frequency refers to the clock signal that is keeping everything in sync inside our devices. Unit prefixes, how much is giga? That's how fast it's switching. All right. So that's sequential logic. Now we get into flip-flops, which always brings to mind the Caribbean or Hawaii. But these flip-flops are not as fun. Well, to me, they are fun. Now, the reason we call them flip-flop is because the output state can toggle a flip-flop between 1 and 0. Okay. So flip-flops are one of the most fundamental devices implementation in logic circuits. Okay. So flip-flop is one of the most fundamental or most basic device. Okay. It can store 1 bit of data or 1 bit of information. Okay. Here is the simplest implementation of a flip-flop. It's 2 inverter gates, and the outputs of each other are fed back as input to the other one. Okay, 2 inverter gates, the output of one is fed back to the input of the other one. The output is labeled as Q. So Q notes the output. So any kind of gates you work with, and you will do that in labs 7, 8, 9. There'll be logic chips in your lab kits. The outputs will be marked either as Q or Q naught. Q naught is also the output, but it's the inverted output. That's all it means. Doesn't mean anything else. Okay. So if Q was equal to 1, let's assume that Q was equal to 1. Then what is Q naught? Q naught is 0, which logically also means if Q is 1, it's being fed back into inverter B, and output will be 0, which is consistent, at the output. And then that 0 is being fed back into inverter A. Its output Q is 1. It's a consistent state. But this is just for explanation purposes, right? We can't do anything with this circuit because we cannot control it. We cannot apply any input. We cannot make any external changes to this, right? But this is just to show you how a flip-flop could work. So a more useful configuration would be using NOR gates. In a NOR gate, depending on the input that is applied, the NOR gate would function as an inverter gate. Okay. So in a NOR gate, you have in a SR flip-flop, you have two NOR gates, A and B. The output of A is fed back as input to B, and the output of B is fed back as input to A. Okay. So this here would be Q. And this here is Q naught. Okay. And the other two inputs that are available are labeled as R and S. And the R and S stand for set, reset. Set, reset. In logic terms, set means you're setting the output to 1. Reset means a reset state, sending it to 0. Okay. The symbol for a flip-flop is a square box. Not a box, actually, technically just a square. All flip-flops are just a square. And the inputs would note what kind of flip-flop it is. So here, this is a RS or SR flip-flop. When I was a student, when we learned it in classes, we used to call it RS flip-flop. But whether you say RS or SR, any engineer would know what you're talking about. Okay, the S stands for set, R stands for reset. Okay, and two outputs, Q and Q naught. All right. So let's begin analysis of this one, right? If R and S are both 0 and 0, well, let's say NOR gate. A NOR gate, what is the truth table for a NOR gate? You have A and actually, let's do input X and input Y. For a NOR gate, the truth table looks like this. If both inputs are 0, output is 1. If both inputs are 1, what's the output? 0. How about 0 and 1 and 1 and 0? You sure? I heard a yes, and I saw a shake. You're not sure? Okay. No, I think Marcus was in the front. But anyway, the NOR gate, both inputs go low, the output goes high. Right? NOR gate is a summation, mathematical summation. So 0 plus 1 gives you 1, output goes to 0. So any of the inputs are high, output will be 0. For the output to be high, meaning logic 1, both inputs must be low. Right? So if R and S are both 0, R and S are both 0, then one of those NOR gates would function as a NOT gate or an inverter. The output would be inverted. But because the output is fed back to the input, let's write the truth table for the RS flip-flop. You have R, you have S, you have Q, and you have Q naught. Okay. Okay. So before we begin analysis, we have to make an assumption on what is the state of the flip-flop. Okay. What is the state of the flip-flop? We don't know what the state is. So let's make an assumption. Let's say Q is initially 1. Okay. So the analysis, assume Q is equal to 1. That would mean Q naught or Q bar is 0. Right? Assume Q is 1. That would mean Q bar is 0. That Q is fed back into B. So 1 is being fed into B. So what is the output of B? If B is 0, A and B are both 0. If A and B are both 0, sorry, not B. If R and S are both 0, R and S are both 0, Q is 1 and Q naught or Q bar is 0. What is the output of B, the NOR gate? 0 and 1. What is the output of B? 0. What is the output of A? R is 0 and Q naught is 0. What is the output of A? So A out is equal to 1. Did anything change from our assumption? Did the outputs change from our initial assumption? No. Our initial assumption was that Q is 1 and Q naught is 0. And we applied input R and S as 0, 0. Output did not change. It stayed the same. Hence, output is Qn minus 1, where N is the state of the flip-flop. So N indicates the current state N minus 1 is the previous state. N plus 1 is the next or the future state. So when R and S are inputs 0, then the output does not change. It stays the same. Hence, we say that the flip-flop has memory. It has stored that data. It has stored that memory. It has stored that data. The previous state was 0, previous output was 0. The output's not going to change. We can prove this if we invert the assumption. If we assume that Q is equal to 0 and Q bar is equal to 1, now if you apply Q bar is 1 and Q is equal to 0, what do you get? Output of B, and this is still the case when R and S are equal to 0. What is B out? B out is 1. What is A out? 0. Our initial assumption was that Q bar is 0. Q bar is 1 and Q is 0. Output has not changed. Input R and S are 0, 0. outputs remain the same as the previous state. They do not change. Let's take a pause and you think over that and let me know if you have any questions. Does that make sense? All right. So now let's look at what happens when you apply R0 and S1. The set terminal S is now 1. Okay. So if S is 1, and I'm going to make changes right here at the top. Okay. R is 0. S is 1. What happens? For a NOR gate, look at gate number B. For a NOR gate, if even a single, if a single input goes high, what happens to the output of the NOR gate? Goes to 0. So Q naught goes to 0. It doesn't matter what happens at this terminal. Here, I'm talking about this. Okay. Gate number B. Gate number B, if S terminal goes high, I mean S is 1, the output of the NOR gate must go to 0. This truth table right there. Right? So if Q naught goes to 0, that means 0 is being fed to gate number A. The gate number A out, Q would go 1. Hence, the flip-flop has been set. Does that make sense? Flip-flop is now set. Q goes to 1. This is 1. 1 and 1. Output is 0. The Q stays at 1. Q naught stays at 0. If R is 0 and S is 1, Q goes to 1. Let's take a pause. Let me know if you have questions. Did that make sense? Right. Now let's do the opposite. Reset goes 1, set goes to 0. What happens then? If reset goes 1, doesn't matter what appears at this terminal, the output Q should go to 0. It's a NOR gate. One input goes high, then the output goes low. So output goes low, that is fed back to gate B, and output Q bar goes to 1. And then 1 is fed back into A, output Q still remains at 0. So if we apply reset terminal is 1, then output Q is reset to 0. Sorry, its output Q goes to 0. Hence, we say the flip-flop is now reset to 0. Okay. So when you apply S is equal to 1, then the output Q goes 1. When S goes to 0 and R goes to 1, output Q goes to 0. And then Q bar is the opposite. So it goes 1. Hence a set reset flip-flop. Did that make sense to everyone? Any questions? Now let's take a pause and analyze what happens. I want you to analyze what happens when both inputs go to 1. If set and reset both go to 1, what happens? Assume Q or Q naught. Tell me what the output is. Yes. That's a possibility. That's a possibility. Yes. That's also a possibility. The real answer is we don't know. And that's why we mark it as not allowed. It would be unpredictable. The output would be unpredictable, and so that wouldn't be allowed. So we'd ensure in the system design that both inputs would not go high at the same time, because we don't know what could happen. Output would be completely unpredictable. So 0, 0, output remains in the previous state. 0, 1, meaning set input goes high, output goes high. If reset input goes high, then output goes low. If both inputs go high, it's unpredictable. It's a race to the finish line. Depending on which electrons are moving faster, output could go high or output could go low. You would not have no idea what would happen. Okay, so hence not allowed. And that's the SR set reset flip-flop. There is something known as the timing diagram that is associated with describing the graphically describing the operation of a flip-flop. Timing diagram basically is time on the x-axis, okay? And we are simply showing a rectangular or rectangular pulses for on, meaning logic high, and 0 when it's off or logic 0. So here's the S and here's the R input. And we need to find the output Q. Okay. And so 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, and then 1. 3, 4, 5, 6, 7, and 1, 0, 1. When set is high and reset is 0, output is high. When set is 1, reset is 0, output is still high. When both inputs are 0 and 0, output remains in the previous state. This is Qn minus 1. The previous state is high. That means this still remains high for the third interval. I think we're out of time, so if you have to leave, you can leave. I'm just going to continue with the example and record till the end. Okay. So again, output Q is high for the first two intervals. The third interval, output remains in the previous state. Then between 3 and 4, output goes to 0 because reset goes to 0. Then at 0, 0, output remains in previous state. So between 4 and 5, it's in the previous state. So it's n minus 1. Between 5 and 6, reset is still high. So the output still remains low. This is Q. Between 6 and 7 is 0, 0, still remains in the previous state. So n minus 1. Between 7 and 8, S goes high. R goes to 0. So output goes high. Then it's 0, 0. So output remains in previous state between 8 and 9. And then between 9 and 10, output is again high. So it remains high. And between 10 and 11, it's again 0, 0. So output again remains high. It remains high all the way until 11. Then when it gets to 11, reset goes high, and so output goes low, and then it remains low because reset is always high. Okay. That's how we would find the output based on the timing diagram. We'd simply take a look at the inputs, we look at the truth table, and draw out the output. Okay. So we'll end class here today, and I will see you all on Wednesday. I will send an email or post an announcement latest by tomorrow night. Okay. All right. Have a good weekend, and we'll see you next week.